All right. Okay, so our next lecture is by Mark Rudner. Hi, Mark.
Hello, can you hear me?
Yep. And so he is joining us from smoky Seattle, from University. Okay, please take it away.
Right, can you see my screen?
Yes.
Yes, okay, great. Hi, everybody. First, thanks to the organizers for putting together this school. It's really great that we can have so many people from all over the world joining at one time and all being together. And also I want to thank Takashi for a really great first lecture to kick off this school and setting up the foundations. So I'll be building on some of the ideas that Takashi presented to us, and hopefully also then giving you a chance to see it in action, and maybe that'll help absorb some of it. And then by tomorrow, maybe you'll have more questions that Takashi or I can address when you come. So Takashi already gave many great references. I put a couple down here to first as a review that my collaborator Netanel Lindner and I wrote a couple of years ago, as well as this other reference, which is called the Floquet Engineer's Handbook. And the second one, this handbook, it's a reference that we started as kind of a living document on the archive, where we put together more of the technical details that it might take to really get your hands dirty and start working in this field. So if you want to try to apply this space-time picture that Takashi was talking about, a lot of it's kind of laid out in great detail there. So we hope that might be useful for you. And we'll be hopefully adding sections to it over time. So I won't be exactly following these references, but many of the ideas are kind of paralleled there. So I think, along with the technical parts, it's equally important to understand, why are we even bothering to pursue this field? What's interesting and important about it? And really, this field of Floquet engineering, Floquet physics, it's driven by really great advances that we've had in physics, both experimental and theoretical, over the past 10, 20 years. Particularly on the experimental side, we've seen the development of a variety of really powerful new tools and techniques for probing and controlling a variety of types of quantum systems on time and length scales that were just totally science fiction just not very long ago. So for example, it's now possible to probe solid state or cold atom systems down to the level of single atoms or single electrons or spins. And also on the, that's on the small scale, but on large scales, it's becoming possible also to coherently control and manipulate quantum states of many interacting components across large devices, like as illustrated by this Google quantum processor. And these capabilities really kind of give us a license as theorists, I'm a theorist, to start dreaming bigger and asking questions that are now physically relevant and testable that previously would have been considered kind of meaningless or just, dreams. At the same time, there have been some really impactful theoretical developments. Maybe most notably for this talk is a new paradigm for classifying phases of matter. Before we always had solid, liquid, gas, magnets, etc. But the idea of topological phases of matter started with the quantum Hall effect in the early 80s, but really got propelled into the forefront of the field in the 2000s with the discovery of topological insulators. And that's really led to transformative ways of changing our thinking as condensed matter physicists. And the combination of all these has also led to a lot of interesting new works about just quantum dynamics of many-body systems, thinking about new aspects of it, in relation to entanglement and all kinds of things that we can discuss. So this is kind of the background which motivates us. More specifically, the question that I'll be addressing in this talk is to ask, what, now that we have this possibility of controlling many-body quantum systems, applying lasers and different types of driving fields, what new types of robust quantum many-body phenomena or even topological phenomena might we find in the context of a periodically driven system? In a way, this has an analogy to what alchemists used to do hundreds of years ago, where they would, by some, who knows what kind of means, hope to turn lead into gold. And we're enlightened modern individuals, and of course, we're not going to try to play with alchemy, and lead is a very toxic substance, so I don't want to get close to it anyway. But we're thinking about is kind of, maybe you could think of it as alchemy 2.0. And instead of just trying to turn lead into gold, we're asking, suppose I have some nice high quality material that was given to me by my favorite grower. By applying a laser or a certain combination of lasers to it, could it be possible that I make this relatively common plain material behave or pick up some more exotic properties or even topological characteristics that I would expect from this more exotic material, also happens to be toxic over here. Or maybe there are some entirely new paradigms of topological phenomena that exist only in the presence of this laser, only in a non-equilibrium driven setting that we didn't even have any analog for, any precedent for in equilibrium physics. And that's what we're going to try to find. And we'll see some examples of that already today. Okay, so this is a series of 2 lectures. The basic outline for today and tomorrow is that, well, first of all, I noticed there was this survey that at least some of you filled out beforehand. And what I can see is that there's a huge range of backgrounds. Some of you have heard about topological phases before, others less so. So I'm going to try to hopefully give something for everybody here. So we're going to start with a bit of a crash course on topology just in the equilibrium setting, just so we have a basis to talk about. If you've never seen topology before, it's only a limited amount of time, so it may be a little quick, but hopefully at least it'll give you the idea and also the tools you need to read on further afterwards, and you'll be able to connect things that I said as you go forward. And for those who have learned about it, hopefully it'll be a good refresher and sort of set the language so that we can have a basis for then talking about topology in the Floquet setting. So once we've established that base, we'll go on to talk about topology in Floquet systems and this idea of micromotion phases. This will all be sort of single particle physics aligned with kind of what Takashi was talking about today, thinking about single particle states and band structures and so forth. This will take us through today and probably the beginning of tomorrow. And then we'll move on to talking about many-body dynamics of a periodically driven system, observables, how are these topological phenomena manifested potentially in experiments, what requirements might we need to see them, and so forth. And I hope at the very end, just sort of for this new crop of Floquet engineers out there, just point out some open questions and challenges that you may be interested in exploring if you want to get into this field. So that's the setup for these lectures, and please do stop me along the way, ask questions. I'll try to monitor the chat as best I can. Babak has been doing a great job, I see, of answering some of those questions along the way in the previous lecture. But it's best for everybody. If you have a question, I'm sure somebody out of the 200 people here has the same question. So just ask, and it'll be good for all of us. Actually, I can test something. By a quick show of hands with the raise hands function, how many people here have taken an introductory solid state physics class, or at least seen Bloch's theorem in some kind of quantum mechanics class before? You can just raise a hand. Okay, so numbers are rapidly rising.
Yeah.
Good. So it seems like
70 and counting. Yeah.
Was that 70 and counting, right? Good. Okay, so many of you, if not, maybe not all, but many. So let me just remind you quickly. So if you have a particle moving in free space through a constant potential, its momentum is conserved. Okay, now if you have, say it's an electron moving through a periodic potential, like in a crystal, then this potential is not uniform. In fact, the reason that momentum was conserved in the first case was that there are no forces. If a potential is uniform, there's no force. Force is the gradient potential. Electrons moving through this crystal, it sees very strong forces every time it moves close to one of the atoms that makes up this lattice. And therefore, naively, you wouldn't expect anything to be conserved anymore. It's bouncing off all those atoms like crazy. But the really amazing fact that was realized first by Bloch in the 1930s is that actually, if you take into account the wave-like nature of the electron, and you ask, how does it propagate as it moves through a periodic potential, as we have in a crystal where the atoms are arranged in a regular pattern, then in fact, there is still something conserved. There's a remnant of momentum called the crystal momentum. And we find that this electron moving through a crystal can propagate ballistically without deflecting forever if it's a perfect crystal. But in exchange for that, its dispersion relation is changed compared to what it would be in free space. And this is analogous to, if you have an electromagnetic wave moving in a waveguide, it doesn't move anymore at the speed of light in vacuum. It has a different dispersion, but it still propagates. So, same idea here. It's electron moving through a crystal, has a new dispersion. We call this the band structure. And that idea has been around since 1936 or so. Now, kind of amazing fact about history is, despite the fact that many very, very, very intelligent people were working on this problem for many, many years, it took almost 60 years until something that we all learned in Quantum Mechanics 1 became widely appreciated in this context, which is that if you diagonalize a Hamiltonian, you get spectrum, a bunch of energy levels, but you also get, corresponding to each energy level, an eigenstate, which is some vector in the Hilbert space. Of course, all these luminaries, they knew about that. But what wasn't appreciated until quite recently, actually, is that if you ask about the motion of this electron, in this material, of course, the dispersion relation plays an important role. The group velocity of a wave packet is given by the derivative of the dispersion. But also, the nature of these eigenstates and how they depend on K. If I look at one K that has some corresponding eigenstate. If I move over to a slightly different K in the same band here, then that'll correspond to a slightly different eigenstate in the Hilbert space. And the way that these eigenstates change as a function of K can actually dramatically alter the motion of electrons in the material. And that's the thing that wasn't appreciated until pretty recently. And this dependence of the eigenstates on K, that goes under a name sometimes of quantum geometry. And much of topological physics, or at least the whole field of topological insulators, is based on trying to understand better the nature of how these eigenstates are laid out in momentum space. So sort of the shining example of all of this is the quantized Hall effect. In that case, we have a two-dimensional system. So the Brillouin zone in that case is actually a torus. It has a kx for the x direction and ky for the y direction. Both are periodic, the Brillouin zone. And from each point in this Brillouin zone, we map to a point in the Hilbert space. So actually, I see there's a question, how do you visualize the eigenstates? So for the purpose of demonstration here, I'm visualizing or graphically representing these eigenstates on a sphere. So if you think of a lattice model, like a tight binding model with only two bands in it, then at each K, the eigenstate is a two-component wave function, like a spinner. So we can think of these wave functions by analogy to spins, and I can always, for a pure state of a spin, represent that state as a point on the block sphere. So there would be, say, spin up is the North Pole, spin down is the South Pole, and I have this state here. If this is a lattice and I have two different types of sites, say A and B sites, then this North Pole would correspond to the wave function point, sitting on all the A sites of the lattice, and the South Pole would be the B sites, and something in between means a coherent superposition of A and B. So that's what this picture is meant to represent for you. I hope that clarified. Right, okay, so in 2D, we have a mapping from every point in the Brillouin zone, which is a torus, to a point on the sphere. And what this really influential paper from Thaulis and co-workers in 1982 showed us was, in fact, that if we consider a few things, actually. So if we consider some little patch of area in K space, that maps to some area on the Bloch sphere. And now if we scan over the entire Brillouin zone, we can ask actually how many times do these eigenstates cover the surface of the sphere? And because of the periodicity, actually, it turns out this is a mathematical fact, which we won't get into during this talk, but you can read more about it. The total area covered by the eigenstates on this sphere as we scan over the Brillouin zone has to be an integer. So this either will wrap the sphere, 0 times, meaning this area has a sign to it. So if it sort of grows and comes back and shrinks to 0, that counts as 0 times. But if it just wraps over the whole thing, that'd be a 1. So the first is a mathematical fact that this quantum geometry has some topological character to it. There's an integer that tells us how many times the eigenstates wrap this entire sphere that represents the Hilbert space. But the physics of it, which is really what's crucial for us as physicists, I guess we're mostly physicists in this room, is that there's a physical property, which is Hall conductivity. That's something you can measure in an experiment. And that Hall conductivity is proportional to this integer that tells us how many times the eigenstates wrap over the sphere. And what's important about this integer, or more generally, any topological index, which is a discrete number, is that an integer or a discrete index can't change by a little bit. It has to change by a lot, a whole step of, from 0 to 1 or something like that. So if you imagine you have a system, has a quantized Hall conductivity in it, you've measured it, and you make some small perturbation. Maybe you add a little bit of disorder, you apply an electric field somewhere. Even though we know from perturbation theory that will change the wave functions by a little bit, it can't change this number, which is the Hall conductivity, by a little bit. It has to be an integer. So that's where the robustness comes from of topological phenomena. And that's what's made them so exciting, is that it's somehow something we can measure, which is very insensitive to details of the sample, to fluctuations, to perturbations. And that makes it more universal in a sense. It gives us many more opportunities to see these phenomena in different contexts. So the last point I want to mention on this sort of lightning review of topological phases is that whenever we have a non-trivial topological phase of matter, say in some piece of material or just somehow realized in some region of space, and then there's a boundary to some other region, which is, say, in a topologically trivial, or even just any different topological state, which is different from the initial one, we'll generically find some kind of protected boundary modes that live at the interface between the two. So in the case of the quantum Hall effect, at the edge of the sample, there's a chiral mode. You saw actually a really nice movie of it in Takashi's talk, which moves only in one direction. So say in his example, it was moving counterclockwise, only around the boundary of the sample. And there's no mode that can move clockwise. That's what makes this thing chiral. So that's a really key manifestation of non-trivial topology. A nice illustrative model that you can go and play with for yourself to kind of see this in action is if you just take, say, a 2D Dirac Hamiltonian and put a mass there, which depends on position, and have it depend on position in such a way that, say, its mass is, say, negative on one side and positive on the other, and you'll find exactly this type of mode that lives in the middle. It's bound to the interface, and you'll find that it moves only one direction. And so as a starter kind of homework problem for you, you're not getting off easy here. I want you, if you have too much time on your hands at least, to try this. Take a simpler 1D version of this, just a 1D Dirac model with a mass domain wall. Say it starts at some negative value on one side, positive value on the other. You can actually make it depend however you want, in between step function, whatever you like. That's something you can solve exactly. And you'll find that there's a mode at exactly 0 energy, and it's localized at the interface. So, give that a shot when you have time, and you'll have seen firsthand what a topological edge mode really looks like. Okay, so that's the end of this introduction. Is there any quick question about that before I move into the Floquet part? No, so it's either 100% clear or 100% unclear. But either way, we're going to move forward.
There is a question.
Okay, one question. Good.
Hi. So you said about this changing integers being robust.
Yeah.
So like integers can also change easily, right? Like,
Well,
like
yeah, an integer can change from 1 to 2 or something like that.
Yeah.
So
yeah, so that can also happen. So
yes, of course. So an integer can change, and I'll show you how it has to change in a moment. But the key point is that if you think about perturbation theory, right? So we have some quantum system, and then you ask, or say linear response theory. If you ever played with that, you have some observable. In this case, it's conductivity, and then we apply a small perturbation to it with a strength. Let's call it lambda, and we can turn that strength all the way as small as we want, down to 0. In usual linear response, we would expect that this observable, whatever it is, will change as we introduce the perturbation by an amount proportional to the strength of the perturbation. So it would grow, linearly. The point is, an integer, if we have to have an integer, so let me just draw a picture here. So here's our observable, let's call it A, and the strength of the perturbation. Linear response tells us somehow it should grow like that. But if we can only have integer values, say 0 or 1, there's no way to interpolate between them like this. Something much more dramatic has to happen. And we'll talk in a moment about what it is that has to happen to allow this integer to change its value.
Okay, thank you.
Okay, great. Right, so I think we should move on. I see there's a couple more hands up, but I don't want to get too far behind. I do want to answer your question, but let's hold them to the end, and then we can come back to them.
And you can submit these in the chat as well.
Yeah, and we have many experts here in the room who can help answer them in the chat while I speak. So I don't want to shut anybody down. I just want to make sure we keep moving forward. So thanks for your interest. Okay, so now let's move into the Floquet part of this. This is a Floquet school after all, and talk about topology, but now in the context of Floquet block bands. So as Takashi nicely introduced, unfortunately, we took the same notation, so that's good. Floquet system, I don't know if he said that word exactly, but it just means a system governed by a time periodic Hamiltonian. Has that property, and capital T throughout this talk at least will always refer to the period of this drive. It's not temperature or anything like that, it's the driving period. And what we learned from Takashi is that at least first, if we think in the stroboscopic picture, like his helicopter that was floating around, the Floquet states are eigenstates of the time evolution operator that propagates the system forward in time through one complete period of the drive. So that's why I say U of capital T. So T is the amount of time of this time propagation. So these Floquet states in the stroboscopic picture are essentially, they look like stationary states, just like the rotors of the helicopter. If I look at time 0, I have this wave function in Hilbert space, it's whatever it is. After one complete period, it's back exactly where it was. So it looks like nothing's happened. That's the sense in which Floquet states are stationary states for the stroboscopic motion. And they pick up phase factors that look very analogous to just dynamical phases that you get in a static system, just from the energy and just waiting for some time. But in addition, also as Takashi told us, there's a so-called micromotion, which is that these states, they're not actually stationary for all time. It's just because we closed our eyes while they were moving. But within each period, there is this, I've used the letter capital phi to denote the micromotion. Each one of these does some loop, moves around through the Hilbert space, but it comes back to where it started. That's why it looks stationary in the stroboscopic evolution. Okay, so that's a picture of Floquet states. One really important point that's going to come up and play a really central role in this discussion is that the eigenvalue, this epsilon here, which looks kind of like energy. If this had been just a static system and you looked at time evolution of an eigenstate, we'd have e to the minus I energy times time is the phase in front. So this thing that looks kind of like the energy, which we call the quasi energy, it has the interesting property that it's not really uniquely defined. Because if I look back here, the quasi energy is defined as, in terms of an eigenvalue of this unitary operator that evolves the system in time. And you see, if I would add, say, 2 pi over capital T to the quasi energy here, then after I've multiplied through by T, I just have an extra, I've added 2 pi to the phase, but actually for this unit modulus complex number, adding 2 pi to the phase doesn't change it at all. So actually adding any integer multiple of 2 pi over T, which is in fact the driving frequency, omega, which is 2 pi over T, any integer multiple of that actually gives me the same exact eigenvalue back. So in fact, this quasi energy, we can think of it as living on a circle. It's like there's a Brillouin zone for energy, just like there's a Brillouin zone for momentum. If I have a periodic crystal potential in space, instead of momentum being a real number, now it lives on a circle in the Brillouin zone. Now we have periodicity in time. Energy isn't a real number anymore. It itself lives on a circle. And this has many crucial implications for the physics of Floquet systems. Just to say one last thing about that, just to give you some physical intuition about it, what this means physically, adding 2 pi over T to the energy, or if we put an H bar here, for those of you who like your H bars, keep the units straight, that's the energy of 1 photon. So what this is really saying is that if I have this driven system, its energy is only conserved up to absorbing integer multiples of the driving field photon energy, or as Nancy mentioned, if it was a mechanical system, it could be phonon energy, whatever it is. We'll just use the word photon here. System has to absorb and emit in discrete quanta, and that's what this circle represents. I see there's a hand up, Fabio.
Thank you, Marcus, for the space. Look, this picture that you are explaining is for spinless particles, right?
Actually, it's very general. It's a general feature of quantum mechanics with a time periodic Hamiltonian. It doesn't matter whether it's spinful, spinless.
So, in thinking about the time of reverse or symmetry, when you put the spin in the contest, you broke it. Right?
Well, okay, so there's a whole discussion we can have about symmetries of driven systems, but yeah, I'm not assuming any symmetry. So we can allow, if for a circularly polarized field, like what Takashi was talking about, all symmetry is broken. There's no symmetry whatsoever.
Right. Thank you for the answer.
Okay, great. Okay, so that's Floquet states in general. Now, if we talk about Floquet states, we have a particle, single particle, it's moving in a periodic potential in space, and it's subjected to time periodicity and Hamiltonian, which is periodic in time, then we should expect by Bloch's theorem that the spectrum of the Floquet operator still has crystal momentum as a good quantum number, because we still have discrete translation symmetry in space, but now the eigenvalues, or the quasi energies, and if we plot them, we should see some kind of band structure, which looks pretty much like a band structure in a non-driven system. Okay, so here's just an example. I drew it by hand, but you can imagine. So we have quasi energy, which is a function of k. It's organized into bands, which are basically the bands of this effective Hamiltonian that we saw in the previous lecture. And this picture, combined with what we talked about in the review of equilibrium topological phases, kind of immediately calls to mind, or maybe suggests to us, that we should start looking for topological phases, topological band structures for driven systems, because we can apply those ideas. We can start thinking about the eigenstates, how are they wrapped up in the Hilbert space as a function of k, to the eigenstates of u instead of the eigenstates of some static Hamiltonian. And historically, these ideas kind of first appeared in the cold atom literature, trying to figure out how to make neutral atoms behave as if they're in a magnetic field, like charged particles in a magnetic field. But then it kind of spread, or was redeveloped maybe semi-independently in the solid state context into all kinds of new directions. And there's a lot of crosstalk back and forth between solid state and cold atom fields along the way. I see another hand, Srimayu.
Yeah, so my question is the definition of this Floquet quasi energy, is it we can define it for all driving frequencies, or it has to be greater than some other scales, energy scales of your system? Because for low driving frequencies, it's not, there is ambiguity, right? Logarithmic ambiguity. In that case, what you do?
So I'm not sure what you refer to as logarithmic ambiguity, but as a formal definition, this is always possible because it's really just a property of the Schrodinger equation. Actually, any differential equation with time periodicity in it, just like Bloch's theorem.
No, my question is this exponential minus I theta, means the unitary Floquet, that one. If you just plot the real part versus imaginary part, that plot. So when for low driving frequencies, what can happen that this near this -1 means the real part is -1, means I am talking about the circle now, and the imaginary part can go to 0, like -1 and 0. There are some states sitting there. So for that, when you take the log means
I see. Mm-hmm. You're asking about the branch cut.
Branch cut, right? So there it's not defined properly. So that one I'm asking.
Great, thank you. That's an excellent question. So there is a branch, there's sort of an arbitrary choice here of a branch cut. So the real eigenvalue is actually this e to the minus I epsilon t, which lives on the unit circle, right? So if we only think about this unit circle, there's no ambiguity. But if we want to switch from thinking about this complex number to a quasi energy, then we have to pick a branch cut and choose, say maybe we put on the negative real axis. You know, are we talking about minus pi or plus pi? What are we doing? And ultimately, you know, you have to keep that in mind and make sure that your answer, your physical answer, doesn't depend on that. And if you do everything right, it won't. I can't say anything more about it at this moment, but in specific circumstances, we can talk what the implications would be.
Okay, so you are taking, means you are considering only situations where this epsilon n is properly defined, or like means means the situations where you are avoiding this kind of branch cut ambiguity for now, or
just assume that some branch cut is picked, and as long as none of the eigenvalues hit exactly your branch cut, so you can pick it in the gap between two eigenvalues, you won't have any problem.
Okay, thank you.
But thanks, excellent question. Okay, so now this picture has motivated us to start thinking about topology of Floquet bands. And you know, one direction of it is really just let's import everything that we know and that the whole community already knows about topology of band structures, because that's super well developed. I don't want to focus on that because that's, you know, something for not a Floquet conference or school. So instead, I want to focus on what's new. What are the new opportunities or new features we can get in a Floquet system that we wouldn't have in a non-driven system? And the key point is that the band structure of a non-driven system really exists on a cylinder. It's kind of inconvenient to draw it that way, but conceptually that's where it lives, because say for a one-dimensional system, crystal momentum K, that parameterizes a circle, but energy is a real number. It can be anywhere from -infinity to infinity. Key difference is that in the Floquet system, we don't have energy, we have quasi energy. And as we just discussed, actually the quasi energy is periodic. It lives on a circle. K is also a circle. So that means the band structure is defined on a torus. And in some cases, that may not have any really important implications, but we can have a situation where as K goes around from 0 to 2 pi or minus pi to pi, however you want to define your Brillouin zone, the quasi energy may also wind an integer number of times, a non-zero integer number of times around its own circle. And that's a feature which has no analog in a non-driven system. There's something purely, it's topological. You see it's an integer, this winding number, and it can only exist in the presence of a periodic drive. So let's try to explore that new type of topology and see what physical consequences it has. And the physical phenomenon related to this, which is, let's say, well known to those who know it well, but now it'll be well known to you also, is something called quantized adiabatic pumping, or shortened sometimes as a Thouless pump. So the idea is the following. Suppose I have a one-dimensional system and it's an insulator. So I have, say, just two bands for the sake of a picture, and I've filled up the lower one. The upper one is empty. So that's why it's an insulator. And there's some external parameters that I can control, and I modulate them very slowly in time, slowly meaning adiabatic compared to this energy gap here. So I don't excite anything, but I modulate these parameters in some kind of cyclic way, so that I start with some parameter settings, I perform some manipulation, and I bring them back to where they started. And the key observation is that for this insulator, I have a bunch of electrons that are sitting here, kind of uniformly spread out throughout this crystal. And if I bring my control settings back to where they started, then at the beginning and ending of the cycle, I have to find electrons in exactly the same place, because it's an insulator defined by exactly the same parameters. But in between, when I've changed the parameters of this lattice, those electrons may have shifted back and forth or moved in some way. And because of this, we see that there's actually a possibility. There's actually only a discrete set of possibilities of what could happen. First of all, it could be that each electron kind of wiggles in its place and just comes back to where it started. Nothing interesting. But for some types of cycles of this modulation, it could be that each one of these electrons moves over to the neighboring location. And because these are identical particles, the initial and final states are indistinguishable. But in that case, we would see that some integer number of charges, of electron charges, actually passed through any point that we choose to look here. And that's what makes this an adiabatic pump. So the simplest model that manifests this behavior, you can take a lattice, 1D lattice with two types of sites in the unit cell, and modulate the sublattice potential. So you call that a capital delta. And we can also modulate the dimerization, which means the relative strength of the two different types of bonds which are here, make one stronger and one weaker. And moving around in this plane by making a cycle here can actually pump charges through it. And so, this is a phenomenon which is known since the early 80s. It's topological, again, because there's only a discrete set of possibilities of how many charges we pump per cycle. But let's take a look at it. How is this manifested in terms of Floquet picture, in terms of a Floquet spectrum? And the key here now connects back to this picture. So this is a manifestation of this new type of topological band structure for a Floquet system, where quasi energy winds as K goes around the Brillouin zone. And so what I want to do is cut open this torus so that we can now look at this band structure in a way that we can more easily visualize. And that's what we see here. So now I've cut open this Brillouin zone. So I have K from minus pi over A to pi over A being the lattice constant. And now quasi energy I've also opened up. And so this band that wound around the torus now just looks like this chiral mode that wraps here.
Just a quick question about the slide with cylinder where you showed. So if we had 2D system, right, 2D Brillouin zone, then it would be again also the usual mapping would be also to a torus, right, with periodic boundary conditions.
Well, okay, so in that case, thanks for the question. So the Brillouin zone itself, as a function of K, is a torus for a 2D system, but energy is still a real number. So it's kind of a three-dimensional cylinder where it's sort of a torus times the real line. And that's still different from what we have on the right, because what's important is that no matter how many dimensions we have in a non-driven system, energy can go from minus infinity to infinity. It doesn't have any periodicity to it. In the Floquet system, we have periodicity in the energy direction, and that's the new feature.
Thanks.
Good. Thanks for the question. Okay, so let's see, how can we see from this picture of the Floquet spectrum that there's a quantized current or quantized pumping of charge that comes out of this system? So it's going to come in two steps. First of all, we're going to look at the average velocity, because if we want to find how much charge moved, we just need to know, what's the average velocity of all the electrons. and how much time did they propagate for, and then we can find out how far they all moved, essentially, and the density of them. So the velocity, we need the group velocity, which remember is the derivative of a dispersion relation. That tells us about the speed of a wave packet. Oh, sorry, let me use a thinner pen. That's the epsilon decay. Okay, that's the group velocity. You learned that in undergraduate mechanics or something. Now let's look at the average group velocity over all the particles in this filled band here. And the key point here is that because of the topology of the situation, that this band, it couldn't just wind around and stop in some random place. It actually had to wind an integer number of times in the quasi-energy direction. The endpoints are basically fixed. So the average velocity is actually, the average slope of this line. And that's exactly, rise over run. It's 2 pi over t. That's the vertical displacement divided by 2 pi over a. That's how far it went horizontally. That's a divided by t. So 1 lattice constant per driving period. Now to get the current, we have to multiply the density times the average velocity. And the density, if we look here, we have, in this insulating state, we have 1 particle per unit cell. So the density is 1 over a. And then we have this average velocity. So that means we have a net current of, 1 particle crossing some cut through the system per driving period. And that's how we can see here this quantized pumping that comes associated with this new type of topological Floquet band structure. And here the number 1 is actually means the number of times that this band wound in quasi energy as k went from across the Brillouin zone. It could have been -1 if this band went that way. It could be 2 if it wraps around 2 times. It could be 0 if I have one that doesn't wind. So it's really just an integer which goes up here, the winding number per period, and that's quantized adiabatic pumping. Okay, so I have a few minutes left before we break for questions. So I want to tell you, actually addressing one of the earlier questions, which was about how does an integer change, or how do we get a topological transition from one topological phase to another? And as I said, a small perturbation can't do it because no observable, at least a topological observable, can't change by a little bit. So the way that a topological transition occurs is actually through a gap closing, or importantly, a point where one or more states become degenerate and then become non-degenerate again. And while they're degenerate, they can completely transform their nature, and then we can have a different band structure when we come out. So in an equilibrium setting, there are many ways to do this by at least conceptually changing parameters. Famous one, which comes back to this Berneveg, Hughes, and Zhang model for the quantum spin Hall effect, is, for example, if you make a quantum well and you change its thickness and you calculate the band structure as a function of the thickness, you would find that start with some value of the width of this quantum well, you have bands and their Chern numbers, that number we talked about before, which characterizes the wrapping of the eigenstates in Hilbert space. Say it was 0, this is a trivial phase. At some critical thickness, actually, those two bands touch. So somehow they were getting closer and closer together. As I change the thickness, they touch. And then if I keep changing the thickness further, they open back up again, a new gap. And in the process, we found that their Chern numbers changed. And now it's in a topologically non-trivial phase. And I've drawn this little edge state in there to sort of indicate to us that it's topological and remind us that at the boundary of a topologically non-trivial material, there's a topological mode there. Okay, so this is the classic view of how a topological transition occurs in a non-driven system. Now, again, really kind of beating on this theme of periodicity of quasi-energy, in a periodically driven system, we have a different possibility for how this type of topological transition could occur. So let's suppose we started in this topologically non-trivial situation that we ended with on the previous slide. Before, the only way these two bands could touch was near zero energy. They come down together. But because quasi energy is periodic in this driven system, we actually also have a possibility that the top of the upper band can touch the bottom of the lower band by wrapping around this quasi energy circle. And that's what's indicated here. So for example, if we change the frequency, then the width of this quasi energy zone will shrink. And at some particular point, actually, the top of this band becomes degenerate with the bottom of that one. And again, this degeneracy allows the eigenstates to totally transform their character. And in this case, we find you can take this as maybe observation for now, and we'll discuss a specific model where this arises. The Chern numbers change to 0. But importantly, first of all, this changing of the driving frequency, we didn't make any degeneracies. Nothing happened in this window of quasi energies here. So the edge state that was there originally is still there. Nothing happened that could possibly destroy it. So in the process, a new edge state was created. And now we're in a situation which, from the point of view of equilibrium physics, would have been totally impossible. So normally, this Chern number is the thing that tells us, is the system topologically trivial or non-trivial? And that also tells me, are there chiral edge states or not? Here we found that in the driven system, even if the Chern number is 0, which makes it look like, at least from the stroboscopic point of view, that this is the Chern number calculated for those Floquet, the stroboscopic Floquet eigenstates. I should have said that. The Chern numbers are 0, yet we still have some kind of topological edge modes here. And so we would like to understand that better. What are they coming from? What is the non-trivial topology behind this? And what are the physical manifestations of these edge states? So in equilibrium, or close to equilibrium, those edge states can help us carry a quantized Hall effect. Here, what kind of physical effect actually will emerge from these new type of chiral edge states? So given the time, I think I'm going to leave it there for today's lecture, and we'll start off tomorrow with an explicit model we can construct. We can just sort of solve it by eye and see very, explicitly where these edge states come from, what's the nature of these bulk Floquet bands, and then discuss the topology of them from there, along with the many-body dynamics that can occur in Floquet systems. So let me pause and just take questions for the remainder of the time.
Well, thank you so much. Very lively and nice lecture. And there are a number of questions. There were some in the chat. So let me see. Maybe I will start with one from the chat, and then we go back and forth between problems. So there was a question by Levi Upreti. If you're there, you could ask your question yourself, or I can read it. Would you like to do that? I don't see Lavi there. Okay, so I will read this. So it says, you showed a picture where there is a mapping between the Hall conductivity and the Bloch-Hilbert space, and the area, the quantization of the area was related to the Chern number. Question is it somewhat related to the quantum geometry concept? And they said that they're not an expert on this. What happens to this picture for second Chern number or higher?
Yeah, so it's completely connected with quantum geometry. So this invariant. So here we talked about this, how eigenstates are laid out in the Hilbert space. So there's an object which is the Berry connection. If you've learned about Berry spaces before, this will be meaningful. If not, well, just hold on a minute and we'll talk about something else. So there's a Berry connection, which is very analogous to a vector potential, but instead of existing in real space, it exists in K-space. And then related to it, there's a Berry curvature, which is the K-space curl of this thing, which is like the magnetic field, except again, it's in K instead of in position. And so this is what characterizes quantum geometry, at least part of it. And this Chern number is actually the integral of the Berry curvature over the whole Brillouin zone. So that's precisely what it is. There are other, that's for the Chern number for, two-dimensional system. no symmetries whatsoever. That's what gives us the topological invariant. There's all kinds of other topological phases which involve different quantities, but this is sort of the simplest, easiest one to understand. So that's why I focused on this one. But you can generalize it in all kinds of directions.
Great. So maybe go to the audience now, and I see a few raised hands. Fabio.
Thank you, Baba. Max, me again. Look, in your last slides, you talked about the topological transition, and you showed the coexistence between the Chiral numbers and this kind of thing with the edge states. In the picture of Floquet systems, how do you classify the universality class of these phase transitions?
You want to ask about the phase transition itself?
Yeah, but look, precisely about the universality class in these driven systems.
Yeah, so I mean that's right. So this would be more akin to, I guess you can think of it like a. So it's not a thermal phase transition like we have, classically. It's more like a quantum phase transition. So phase transition, property of thermodynamic system. There are many subtleties there in a driven system associated with what are steady states, what happens in a many-body setting. We can characterize it, for example, if we want to make analogy to the quantum Hall transition, there, we can ask about how, it's actually something I'll talk about tomorrow, how the localization length diverges as we approach the transition. And that is something which can be also applied to the Floquet states, and we've actually done it in this context. And the critical exponents there seem consistent with quantum Hall transition. So in that sense, it seems to be consistent with same universality class as a quantum Hall plateau transition from the localization point of view. But it's a very interesting subject, which I think has much work still to be done there.
Right. But so you are saying to me that for the driven systems, the concept of universality class, you make do a correspondence with the equilibrium one?
Well, not thermal equilibrium, but we can say maybe at T equals 0 or ground states, because like quantum phases, because generically the steady states of the driven system are not thermal states. So we can't exactly map it like that. But in this case, for example, if you ask about localization properties of eigenstates, that can have a close analogy to what we see in quantum Hall transitions, the function of energy as you sweep through the spectrum, something like that.
Right. Thank you for your answer.
All right. So maybe I'll read one more question from the chat. Ali Fahimnia, are you there? Do you want to pose your own question?
Yeah, I can answer the question.
Yeah,
so my question is about the 1D model with dimerization and staggered potential. So in the Floquet band that you're showing, you say that these are in the next slide, you said that these are the occupied states that move in one direction.
Mm-hmm.
Is my understanding correct that the unoccupied states would move in the other direction? Like from
yes, exactly. So remember that we started with this 2-band model here, and I said we occupied the lower band and the upper one was empty. That's why it was an insulator. In fact, if I would plot the empty states, those would correspond to a Floquet band with the opposite chirality, because there's actually a sum rule that the sum of winding numbers of all the Floquet bands has to add up to 0.
Yeah.
Similar to the Chern numbers of all bands always adding up to 0.
Yeah. Then by just looking at the Floquet bands, let's say I go calculate the Floquet Hamiltonian and then look at the bands. Is there a way to find the occupation numbers by that picture and not going back to the stationary picture? And then knowing that, okay, by the occupied state are going to move to right or left or not?
Okay, it's a good question. So occupation numbers is the property of a many-body state. And in equilibrium, we have a principle, which is, say, if we go to 0 temperature, minimizing energy. There is no such principle in a driven system. So then it's a non-universal question of how did these states get occupied? If it's cold atoms, maybe some very experienced experimentalists could load them by demand into one band or the other. If it's a solid state system and there's phonons and whatever else there, then there may be some steady state that's obtained, but it will have some potentially very complicated form, which is non-universal. And hopefully we'll have a little bit of time tomorrow to discuss some basic aspects of that.
I see, thanks.
All right, maybe one more question from Srimai.
Yeah, so my question is, you said this topological protection, it's robust under perturbations. So now if you just apply one perturbation which breaks the symmetry which you initially have on means in your system, in that case, what will happen? This symmetry breaking perturbation will give you protection, or it will break such protections?
Okay, so the question is about topological phases that are protected by some symmetry. In that case, if you apply a perturbation which doesn't respect the symmetry that was protecting you, then all bets are off. So for example, if you have a quantum spin Hall system, which is protected by time reversal symmetry, and you apply a magnetic field, then there's nothing left, strictly speaking. Here, quantum Hall, and also this case that I illustrated at the end, are particularly robust because there are no symmetries other than time periodicity of the Hamiltonian that preserve them. So that's why they're protected against almost all perturbations, except for those that break the discrete time translation symmetry, so noise essentially. And then what happens with noise, if you don't have perfect translation symmetry in time, you may find that it's still something survives for a long time, potentially a very long time, but not for infinite amount of time, because eventually it can break down.
Thank you. Thanks for actually answering my follow-up question, because I am going to ask that. Thanks.
Thanks.
All right. Well, thank you so much, Mark. I think we're good on time. And thanks, everyone. So we will take a short break. I suggest that we come back at the scheduled time. So that will be like 8 minutes from now. 10 past the hour, or if anybody's on a half-hour time zone, that will be 20 to the hour. All right, so we'll see you in a few minutes.